wonder what a flying car looks like and how it works? Or are you interested in pursuing a career in STEM but just don't know where to start? Or are you just looking for a meaningful way to spend your dream holiday? Learn from some of the best in the aviation industry as they share their amazing career and the exciting experiences that they have. Explore with innovators and entrepreneurs as they come up with exciting technologies to revolutionize the field. And hear from educators who bring science to life through experiential learning. Aspire Week is here to inspire you. Join us online from 14th to 20th June. See you soon.
Hello and welcome to Aspire Week, where we explore flying cars, innovation and technology, and careers within the aerospace industry. In this session, we have Mr. Simon Gwozdz, founder and CEO of Equatorial Space Systems. Simon, welcome to the show.
Thank you so much, Johnson. Great being here. Thank you for having me.
You started Equatorial Space Systems, ESS, when you were an undergrad. What were you?
I did. Yeah, I did. I was very unfocused on my academics. So I was always looking out for various other things to do in my life. And I was interested in space tech since I was a kid. So being an undergraduate, I thought that if I'm ever going to jump into that field, then this is the right time to do it. And I started by interacting with the local space tech ecosystem. Believe it or not, we actually do have one. And as a result, I was able to identify some pressing market concerns. And at the same time, I was doing some self-studies to understand this topic better, and especially some of the key engineering concepts involved. So that was it. That was the start.
What was the rush? I mean, you were an undergrad. What made you think that you had to do it there and there? Was there an opportunity that you saw that you couldn't refuse?
If not now, then when? I think you will see that from entrepreneurs in general. The same, why wait if you can just get started right away? And sure, things may not work, but you will learn a lot in the process. And so far, I'm pleased to say that Equatorial Space is going pretty strong. And we're on the right track to become the first commercial space launch service provider in Southeast Asia. So,
fantastic.
Yeah, that'd be pretty awesome.
Fantastic. Well, very interesting. I'm sure all this is looking forward to learn more from your experience, both from a space point of view, your insights, as well as your entrepreneurial journey. So I shall now leave you to share more, and we'll be back with you at the end for Q&A. Over to you.
Perfect, John. Thank you so much, Johnson. We'll be delighted to share. So the topic I prepared for today is not so focused on the entrepreneurial experience and adventure that it was so far. I wanted to instill some of the key fundamental concepts into our viewers today, which are involved in launching satellites into space. So, well, I suppose a lot of people are quite curious about the field of space launch and of what we call collectively new space. It is very popular nowadays, but how does it actually work? Now that is where a lot of people I've met were not as clear anymore. So hopefully today I'll be able to provide you some very valuable insights and also some very basic concepts, which are without the basics, there's no point moving forward. So really, that's what we should get out of the way first. So I assume that viewers today would have some background in physics, some basic background in physics, so they can better understand the concepts. But if you have any questions, not just about the engineering or the technology or the science behind all of this, but also the entrepreneurial experience, I'll be more than delighted to share towards the Q&A session later on. So first of all, and yeah, it's as basic as it gets. Let's define what space actually is. And the most common convention to define space, the boundary of space and the atmosphere, is at around 100 kilometers in altitude, which is basically in so-called thermosphere, right? And that is not a completely arbitrary number, actually. I'll get to that very shortly. And for lack of a better term, space is mostly made up of vacuum, mostly made up of nothing. But there is still some very distinct environmental considerations between different areas of space. The environment that you experience in low Earth orbit will be very, very different than the environment that you can expect on the lunar surface. The radiation is different. The low Earth orbit satellites are protected by radiation by the so-called Van Allen radiation belts, which are basically created by the magnetosphere of the Earth. And of course, there's things such as solar winds, solar radiation pressure. All of those different forces and different effects have different levels of significance depending on where you exactly are. So I just want you to understand that there is no such thing as just saying that, well, if something works in space, then it can work, anywhere around that space. No, spacecraft that are designed very specifically for the exact environment that they are actually going to be operating with. But now let's also have a quick look into what is the actual definition of an orbit. So among people who are not fully clear about the difference between orbits and space, there is a lot of I've noticed that some people use those two terms interchangeably. That is just completely wrong. So let me just get that right out of the way straight away. Imagine yourself standing on a very high mountain, and it's a very high mountain so that you can disregard air resistance. Simulate the environment that you can expect from low Earth orbit. From the altitude of around 300, maybe 400 kilometers. Of course, we don't have mountains that high, but just for an illustration's sake, let's imagine that we are actually standing 300 kilometers up and holding a cannon, like those medieval cannons, aiming to launch a cannonball with black powder out of it. And that analogy is actually known as the cannonball analogy, and it was first made by Sir Isaac Newton. The faster you launch that cannonball from your cannon, the farther away it's going to fly. That's logical. That's perfectly easy to imagine, right? And the faster you launch, and if you launch it fast enough, at some point, you're going to send that cannonball quickly enough that it will go all the way around the planet and return to the same spot. And that is an orbital velocity. And in case of the low Earth orbit, the velocity you actually have to hit is around 8 kilometers per second. So now let me backtrack a little bit to the definition of space. If you're a Kármán line, and if you're traveling with a normal aircraft, an aircraft that generates lift with an airfoil, right? I suppose you understand the concept of airfoil. The pressure differential basically produces lift. But the higher you are, the less air molecules you have to actually produce that pressure differential that's required to produce sufficient lift. And at one point, and to compensate for that, you have to travel faster so that the flow rate around your wings, around your airfoil, is actually increased. And the Kármán line is an altitude at which, to maintain lift, you have to basically travel at an orbital velocity. So that's why the Kármán line is not an arbitrary number. It just happens so that it's very close to 100 kilometers. And that's why most people, for simplicity's sake, will be referring to the boundary of space as 100 kilometers. But of course, things are not as simple, and I will get to that very shortly. So that's why velocity that goes sideways is actually more important than getting to the right altitude. The only reason we need altitude is to escape the air resistance. That's why rockets, that if you've seen those live feeds from SpaceX or NASA, or recently from China, you would have realized that rockets only go upwards for a very short period of time. And after that, they conduct what we refer to as a pitchover maneuver. And then they start to produce that horizontal velocity. And that horizontal velocity is what actually makes you stay in this perpetual movement. You're still attracted towards the planet, but you're traveling so far sideways that before you hit it, you basically miss it. You're already on the other side. That is an orbit. And the only reason why we need to build up that altitude is to prevent objects from being slowed down by the atmosphere and just re-entering right away. Now, another thing which I want to make very clear is that objects in orbit travel around the center of the planet, or rather the barycenter of the mutual pull between the two of them, because, well, as we know, everything has gravity. Everything that has mass will produce some gravity. But for simplicity's sake, satellites are so small in comparison to the planet they are orbiting that we do not really consider that effect of the satellite's gravity. But still, they are traveling around the center of that planet, so they cannot just stay over the northern hemisphere or southern hemisphere, for instance. They will, regardless of their orientation, actually cross the equator. And that is a very important concept that we call the inclination of an orbit, how inclined it is. An orbit which is in a 0-degree inclination would just pass by right above the equator. An orbit which is in a 90-degree inclination, as the one you can see right over here in yellow, would be passing over the entire surface as the planet underneath rotates, right? Hopefully you guys are still with me. The idea is that the orbit doesn't really shift. I mean, it does. There are some effects that do make it shift over time, but in a short period of time, like a few days, that effect is quite negligible. So as the planet underneath rotates, the ground track shifts every single orbit. That's why you can see those sine curves on this illustration right over here. That is actually the ground track, because the satellite's orbit stays more or less fixed, but the planet underneath rotates. And this produces an effect known as a revisit rate that a satellite can actually produce, and also and the ground coverage that a satellite can produce. And that is extremely important, because some satellites need to be in polar orbits because that's what their mission requires them to do. They need to do scans, scientific scans, for instance, of the entire surface within over a span of months, of weeks to months. But some satellites, which are supposed to provide some specific service to countries which are right next to the equator, for instance, do not actually have to go all the way up to a polar orbit, as we refer to, which is what a 90-degree inclination will basically provide you. And well, as you can see, the revisit rate of polar orbiting satellites is pretty poor, but the one for equatorial satellites is actually much higher, even though they don't go as far north and as far south, because, well, their inclination is lower, right? So that is why various missions really have different requirements in terms of orbital parameters, depending on who is the actual user of the data or the connectivity that satellites provide. I will get to that very shortly. Of course, real life is way more messy compared to the theoretical model, and satellites in pretty much any trajectory, any kind of orbit, will experience what we call perturbations, which is just net forces acting on them, right? The gravity of the Earth is not constant. I mean, it is constant, but it is not equal in every single latitude. The Earth itself has some well, it has an irregular shape, actually. It's not a perfect sphere, and that changes the gravitational acceleration depending on the latitude, and that itself can actually move the satellite's orbit. There is traces of air resistance in low Earth orbit altitudes. That only becomes negligible maybe around 600 kilometers plus. There is still forces that act on all those satellites, and that's why sometimes satellites require to change their orbits during the mission or conduct what we call station keeping, which means to fire a thruster to offset those net forces acting on them, right? And that's what the International Space Station is doing, for instance. If it wasn't for an onboard thruster that they fire roughly once a month, the ISS would have already deorbited itself because of the very small amount of air resistance at the altitudes of around 400 kilometers. It keeps slowing them down, which is referred to as orbital decay. And yeah, that's the kind of environment that you can expect from space. It's nasty. It's not easy to deal with. And of course, gravitational forces of Sun and the Moon do have an impact. To a lesser extent, gravity of Jupiter will have impact on you if you go to a certain distance. That's the third largest generator of gravitational perturbations in near space environment, basically, even though it's super far away. And you have to consider all of those small little things in your mission planning, which is really difficult. And I could speak about that for another occasion, but for now, this is all I'm going to cover about the nature of orbits and some of the key considerations for spacecraft. Now, why are orbits useful in the first place? That really has a lot to do with the field of sight that you receive from a high altitude, right? An aircraft that travels at around 11 kilometers in altitude, and that's a typical cruising altitude for an airliner. From that position, you can see around 400 kilometers in every direction. That's the kind of radius that you can produce, which is quite a lot, actually, if you think about that. You can cover an entire country with a transmitter that's on board of an aircraft. If you take it a step further and you develop a high altitude drone or a high altitude balloon that's supposed to stay up for a while and provide some sort of, let's say, connectivity service, you can roughly get 700 kilometers radius. But a satellite orbiting at 400 kilometers, roughly 400 kilometers, will actually give you a field of sight that's, well, more than 2,500 kilometers wide, right? So that is a beautiful thing that comes with satellites. Also, satellites are not, well, they don't require, in fact, they are designed for that because for obvious reasons, they do not require maintenance. They are just easier to operate and cheaper to operate once they're already deployed. And they are also completely impervious to weather conditions. Of course, some of the data may be attenuated by water vapor that's being streamed. I mean, that's present in the area. So that is a concern. But the satellite itself will not actually be affected by it. And that's why satellite constellations, which is just another way to say satellite networks, can be a very convenient way to provide literally two things. That's what commercial satellites do: connectivity and geospatial data. Satellites are our eyes and ears in the skies. Without them, our civilization is going to be quite severely crippled. We will not be able to navigate as efficiently as we are right now. We will not be able to communicate. We may not even be able to withdraw cash from ATMs because that's ATMs are actually connected to satellites for a variety of reasons. So there's plenty of things that we use them for already, and it's definitely not an area of science fiction. Satellites are very much used by pretty much every single industry right now, and that is only going to get more and more interesting. And satellites are actually changing quite a lot these days. Back in the 60s or 70s, a satellite would be as big as a school bus. And that's really to reflect the sizes of computers which were available in that era. The mainframe computers that literally had to occupy an entire room to actually provide you with several megabits of computing power. And the exact same thing was true for satellites. It would take hundreds of millions of dollars to build those satellites, qualify them for flight, and actually launch them. Nowadays, satellites are more like shoebox size. A lot of companies are building satellites which are as small as mini fridges or shoeboxes, or maybe at most the size of a small car, as opposed to a bus. And that really reflects the changes that we have experienced and witnessed in the electronics industry in general. And that effect of new generation electronics, which are getting smaller and more powerful and more robust and more affordable, has of course been affecting the space tech industry. So nowadays we're moving from so-called old space to new space. Instead of having one single satellite in a geostationary orbit, which is very, very high up at 36,500 kilometers above the surface, at that point, the satellite takes exactly one full day to complete a revolution around the Earth. That's why it's useful, because it appears to be fixed over the surface. So instead of putting one satellite like that, which is huge, bulky, and just generally quite inefficient, contemporary satellites can cost as much as a few $100,000 to make. In fact, you can find components for them in the internet, which is just incredible. That was unimaginable 20 or 30 years ago. The total industry size is growing very quickly as well. There's, depending on who you ask, between 8,500 individual small satellites coming up in the next 10 years. Some companies think that number can actually grow to up to 40,000. So satellites are really becoming much like smartphones of the skies, rather than just eyes and ears. They are so versatile, and they are so useful for a variety of industries to make their processes more efficient, and they help us understand each other and communicate much better. And that the number of small satellites which is going up, and the nature of their formations. Instead of launching one single satellite into a particular orbit, you want to distribute a number of them into a bunch of different orbits to make sure that you have continuous coverage near the surface of the Earth, for instance. That is why there's a growing interest in so-called dedicated launch service. Companies such as SpaceX offer what you could think of as a container ship service, but some companies are more like FedEx, and that's exactly where we are situated. We are going to be offering a dedicated service into a specific orbit, because changing your orbit after launch is a very it's a very inefficient maneuver. Also, satellites are getting more and more satellites are deployed in a so-called low Earth orbit, and that's done for a variety of reasons. So the image you can see right over here, that's actually from one of the online resource websites on present satellites. The red ones are dead, the green ones are operational. You can see just how many of them there are. There's a couple thousands of them. And you can see that the geostationary altitude, which is right here, that band of green operational satellites, is actually very congested. It's not easy to secure a slot to deploy your satellite in that particular orbit. It's expensive to even secure that. And on top of that, it's also very expensive to get there, because you basically have to reduce the capacity of a launch vehicle to roughly 1/3 of what you could carry to low Earth orbit, and you still have to pay the same price. So that's why satellites, which are themselves getting way cheaper, are more commonly deployed in lower altitudes. There's a couple of benefits to that, aside from the congestion fact. It lowers the launch costs. It's much closer to the surface, of course, so the latency of communications gets drastically lower. You can send more data using the same amount of electricity back and forth, and that is why applications such as satellite internet are becoming practical with low altitude orbiting satellites. Because right now, if you launch them into geostationary orbit, then they are going to be pretty much useless, or maybe not useless, but really painful to deal with. Geostationary orbits are mostly used for TV broadcasts if you need to have coverage of large area, and you don't need a two-way communication. Just send one signal and then broadcast it. Then that's a perfect application for them, and that's not going to go away anytime soon. But for novel applications such as internet, IoT communications, etc., that's where low Earth orbit is vastly more practical. Also, low Earth orbit, as we have already established, does induce some orbital decay effect because of traces of air resistance. So lucky for us, space debris is not a serious problem in low Earth orbit, because there is a natural cleansing effect going on at those altitudes, right? Even if a satellite does not have a means to maintain its orbit with some form of a propulsion device, it will just deorbit after 2 or 3 years typically. Right, so now, why is it so hard to actually get a satellite into orbit? And this is where we go a little more into the mathematics of it. So the idea of total specific energy comes into picture. By total specific energy, we're talking about, well, in this case, just kinetic and potential energy. We're not going to really jump into thermal energy and all of that. So this is, really secondary school level physics. So kinetic energy is generated by your speed, the fact that you're in motion. And potential energy is generated by the fact that you're high up above the surface, or at a particular height in general. And of course, we take the specific energy in this case, so we divide that by the total mass of an object, just so that we have an apples to apples comparison in how much specific energy do you need to introduce to a satellite, for instance, or to any object to get them into a specific situation. If you're traveling on an airliner, your specific energy will be around 0.144 megajoules, which is quite a lot compared to being on the surface. And that energy all comes from the chemical propellant on board, from basically from the jet fuel that the engines later convert into altitude and speed. In case of a suborbital rocket trajectory, and a suborbital rocket, just to quickly explain to you, goes up, but doesn't build up the velocity required to enter an orbital movement. It just goes up, then it stops at the peak altitude. We call it apogee. At apogee, it basically stops and then starts falling back down. So at the point of apogee, at 400 kilometers, you'll have a specific energy of roughly 3.9 megajoules. But a low orbiting satellite at the same altitude will have 33 megajoules of specific energy, which means that the altitude only adds up to maybe 11 to 12% of the total energy that you have to introduce into the system to actually deploy it into a low Earth orbit. In case of geostationary orbit, which is again way higher up, at around 36,000 kilometers, your specific energy is close to basically at 362 megajoules. So yeah, it's quite a drastic increase. And that is why rockets are just so incredible, because the only way to really build up that kind of velocity is with a device that converts some other form of energy into kinetic and potential energy, right? And does it quickly enough to offset the gravity directly. The thrust that it builds must be higher than the force of gravity acting on it. Otherwise, you're not going anywhere. And that device is basically a rocket, right? So rockets, from the scientific perspective, take the chemical potential energy, which is stored in the propellant, and propellant is made up of two different things: oxidizer, which provides oxygen, and fuel. Those are the two out of three things, including fire, that you need to maintain combustion, right? Again, the triangle of fire. You need temperature or source of ignition in this case, you need a source of oxygen, and you need a fuel, something that actually burns. And rockets carry all of that stuff inside. So they need to store all that energy themselves, and then they burn it inside of the engine, at which point that chemical energy is converted into heat energy. And then a nozzle, which actually directs the flow of those hot exhaust gases, converts all that heat into a kinetic energy. Right, and that's why the exhaust gases propel the rocket upwards, in the opposite direction, basically. Now that's your Newton's third law, basically. Was it third or second? Never mind. So the idea of thrust is very simple to understand. Thrust is made up of three components, right? Mass flow rate, which basically means how quickly do you eject stuff, what's the mass per second of the stuff that you're throwing behind you, and the exhaust gas times the exhaust gas velocity, which is how quickly does it actually fly out of the engine, and that is the force that you're producing. But also there is a little extra thing which is called the back pressure, and that is caused by the ambient air pressure acting on the nozzle and squeezing that exhaust gas flow, right? So that's why, for that reason, rockets are always more efficient in vacuum action. Don't let anyone who believes the Earth is flat try to tell you that rockets cannot operate in vacuum. In fact, they do. They carry their own oxidizer, so they are not air breathing like a turbofan engine, which gets the oxygen from the ambient air. And as a result, if you're operating in vacuum, then basically this entire thing over here, that expression basically becomes zero. So you actually get a higher exhaust gas velocity and therefore higher efficiency of your entire system. Also, rockets make it pretty. I mean, there is a very easy equation, reasonably easy equation called the rocket equation, which determines how much velocity change can you produce from a particular rocket system, and that's the point number 2 over here. It's basically exhaust gas velocity times natural logarithm of the so-called mass ratio, which is the initial mass divided by the final mass. And of course, as we already established, to actually lift off, a rocket must produce quite a lot of combustion products quickly, so that the flow rate produces a thrust level that's sufficient to counteract the force of gravity immediately. Which is why chemical rockets are the only way to launch something into space right now. Sure, you can build an electric thruster that uses some noble gas accelerated to a very, very high velocity to produce a very efficient stream of atoms, but that is not going to provide you more with maybe a few millimeters of thrust, even though it's a very efficient method. That's why chemical rockets are the only way to actually work in space launch applications. And well, as we already established before, you need velocity change of around 9.5 kilometers per second to enter orbit, to 8 kilometers per second of the actual velocity. And the rest goes into counteracting the force of gravity and also the force of air resistance during the ascent phase. right? So that's why you need to basically build you need a lot of energy to actually counteract all those forces and build up the velocity required to enter orbit, which is why rockets are so freaking big. Pardon my French, but they are really, really big. Only around 1% of a typical launch system is actually the payload. Out of the rest, around 90% is actually made up of the propellant mass. Only around 9% of the rocket is the structures, engine mass, and all of that. That's the kind of margins that you want to achieve when you're working on the rocket system, right? And of course, you need to carry as much energy inside as possible. You don't want to be using things which are not dense. That's why lots of rockets carry cryogenic, so-called cryogenic substances like liquid oxygen, and cryogenic just means super, super cold to keep them as dense as possible. The most commonly used oxidizer, for instance, is liquid oxygen, and liquid oxygen is stored around minus 183 degrees centigrade, right? And it would actually be easier to burn pure gaseous oxygen, because this way you have a full combustion efficiency. You don't have to break that up. You don't have to break a liquid flow into individual atoms to achieve full combustion. But then again, that would mean that you have very, very little oxygen on board. So that's why cryogenic storage is such a common solution. So now, how do we actually deliver all that energy into the nozzle? Okay, that is the whole point of rocket science and rocket engineering, in fact. And yeah, I would love to spend more time discussing various engineering choices and options available, but I'm going to just quickly run through 3 broad types of rocket engines. So first of all, the kind that most of NASA rockets use and SpaceX and a bunch of other companies are using is the so-called liquid rocket engines. And liquid rocket engines carry liquid oxidizer and liquid fuel, and then those two things are supplied into the combustion chamber through either a highly pressurized system, which makes things simpler but also heavier because you have to make sure that your tanks are stronger, or through a system of turbopumps, which is most commonly used for booster applications, for the more powerful first part of the rocket, right? So, well, anytime you actually, any product that involves a turbopump is insanely complicated. So that's why liquid fuel rocket engines are so notoriously expensive. A single Merlin engine costs around $1.2 million to build. And that seems to be pretty consistent among the newer companies working on newer systems. But also liquid fuel rocket systems, well, they carry most energy and they provide the highest exhaust gas velocity. Like the most efficient combination is liquid oxygen and liquid hydrogen. Liquid hydrogen is even colder, so it's an engineering challenge. That's why most companies stick to kerosene, or recently methane. The other kind, if you ever had the chance, not in Singapore, of course, but overseas, to deal with fireworks or small amateur rockets, you would have played with what's referred to as solid rocket motors, right? So solid rocket motors basically combine the oxidizer and fuel in a solid form. A good example is a so-called HTPB rubber and ammonium perchlorate. Ammonium perchlorate is an oxidizer in this case, and they are basically casted together into a solid form. Once you light it on fire, it just goes. There is no moving parts in this thing, unless you introduce some form of thrust vectoring to steer that rocket in a particular direction. But for lack of without that kind of motors basically don't involve any moving parts, so they are very simple. Depending on the solid fuel, they can be stored for a very long time. They can be ready for flight immediately. That's why most missiles in the military are solid-based. They don't require time to prepare them for flight, and that involves both tactical small missiles and intercontinental range missiles. And the problem is that it basically involves a very, very significant explosive hazard. So you're dealing with high-powered explosives. Solid rocket motors are simpler, but they are not necessarily cheaper compared to liquid propulsion technologies because of the costs associated with all the safety precautions of manufacturing them, storing them, and transporting them. So they are not a perfect solution. And the third type, which is less commonly known, is what we refer to as a hybrid rocket motor. And hybrids are pretty interesting because they carry liquid oxidizer and solid fuel. They don't require a detonation going on inside of the combustion chamber. They rely on deflagration. Once you supply the oxidizer through the solid fuel, through the opening at the center of it, it starts to burn. And then it produces the exhaust gases, which are then directed through the nozzle. And in this case, the solid fuel is actually non-explosive. It's perfectly inert. And hybrids are pretty simple and affordable. You can build an engine for a couple of $1,000s. In fact, people have been doing that. Even one person I know in Singapore built an amateur version of a hybrid recently. But historically, hybrids have been always limited by the performances of the solid fuel technologies which were available. Basically, that solid fuel did not burn quickly enough. And that was always the problem why, even though hybrids are not a new idea, they never found commercial applications in space launch. And well, so now what's wrong? What's exactly wrong with space launch? Well, we have a pretty difficult combination to deal with right now. The cost of launching small payloads is still very, very high. Don't let SpaceX fool you with $3,000 per kilogram kind of pricing. The price that the client ends up paying is typically closer to 40 to 80,000 per kilogram for small satellites. Only if you have a very big one that weighs a couple of tons, then it brings down your average price down. Also, rockets are still very dangerous. The average launch failure rate is around 6% right now. Some launchers, such as Electron, the one on this picture right over here, that's actually New Zealand, by the way. So countries with reasonably small economies are also jumping into this whole bandwagon. So Electron has a failure rate of close to 12%. And that's supposed to be a premium product. That's charging extra for a dedicated launch at the correct schedule and into the correct orbit that clients specified. If 12% was the failure rate of a commercial airliner, I don't think any one of us would want to fly. And also, because rockets are still just so complicated, there's a lot. They're notorious for plenty of delays, and that is not a good thing from the business perspective. So this is exactly why we are working with the technology that we've got. We have a proprietary solid fuel that makes hybrid rocketry competitive with liquid fuel and solid fuel rocket systems. Why is that important? Because we can build something the size of a Falcon 9 with this technology for half the price. And we can still maintain the same functionality in terms of reusability if we wanted to. But right now we are still doing prototype tests. What you see right here on the right is actually the very first commercially built rocket in history of Southeast Asia. We launched it last year in December in Malaysia with our Malaysian partners, whom we are super grateful for helping us out with all the necessary arrangements. And basically, this rocket does not contain, the propulsion system of this rocket doesn't contain anything that's explosive. So if you're wondering how on earth can we work on rocket systems in Singapore, which is super restrictive on all forms of explosives, well, we don't use any. That's the beautiful thing. And of course, simplicity of the whole propulsion system makes those rockets very straightforward to produce. And we will soon be starting our suborbital missions with a much larger rocket that uses the same technology. And our aspiration is to start orbital launches with a much larger one, of course, from 2023. And in the process, reduce the cost of launch by roughly half compared to similar vehicles. Now, why are we doing all of this from Singapore? Singapore has a pretty nice location, very close to the equator. In fact, it's enshrined in our very company's name. And launching from the equator means that you can actually choose any inclination and do a very efficient launch and serve any client who has any requirements in terms of any target orbit without conducting any additional maneuvers after the launch, which is really a big problem. Equatorial inclinations are very popular now. I mean, they will become very popular because they offer a very fast revisit rate. Every 90 minutes, the satellite will be over the same spot. And countries such as, well, Indonesia, of course, Kenya, Tanzania, parts of Brazil, no, they don't need to put a satellite into a polar orbit if they can do it, put a satellite into an equatorial orbit. And that's the kind of market niche that is currently unmet. That's what I realized when I first started interacting with people in the space business. And of course, Singapore is pretty close to those places, which could be very helpful for sea launch. We are not going to set up a launch pad at Changi Airport. Don't worry, that's not going to happen. No, that would just be a little too risky, even with our technology. But sea launching has been done before by a number of organizations, and that's exactly what we plan to replicate with ourselves. And it's pretty nearby, so the logistical costs would be reduced. Now, why should Singapore bother with space in the first place, right? That's a question I very often get. And the only answer to that is, why bother with anything else? Why bother with the port of Singapore? Why bother with Changi Airport? Why bother with MBS or Jurong Island? space is a major industry that's growing very quickly, and the barriers to entry have been lowered radically in the last 10 or 15 years. It would be foolish for us not to jump into this opportunity to make a name for ourselves. It would also we can follow the lead of other countries which are relatively small and have been very prominent in the new space game, like Luxembourg, for instance, which introduced a very favorable set of laws to support space exploration activities. And plenty of companies have been actually moving there for that reason. That's something we can easily replicate, aside from having a very convenient place to actually, as a staging base for actual launch operations. Also, space is the future, of course. There will be things like space mining, space tourism, plenty of potential economic value in that, built trillions of dollars. And in space, our initial limitation, the size of our landmass, is no longer going to be a problem. It doesn't matter how small your country is or how big your country is. All that matters is how good is your technology. And that's why we are working very, very aggressively into meeting pretty tight deadlines to make sure this actually happens in a timely fashion. But also, I would like to offer you some food for thought before I finish. This picture was taken from around 6 billion kilometers away from Earth. And you can see Earth here as just one small pale blue dot right here. That picture made me think some time back that we are not talking about traveling to space. That's a misnomer. We're not traveling to space. We all already are in space. And without knowing how to deal with this environment and with our neighborhood, we are no better than dinosaurs. And that's why space is important. And thank you very much for your kind attention.
Thanks very much for that, Simon. I thought that was a very good, compact crash course space rocket launch 101 sort of.
It's a simplified one, of course. Yeah.
Yes. Yeah. That will be very apt for the crowd. So we have some questions, starting with this one. Do you foresee commercial suborbital travel becoming commonplace in the future?
Yeah, absolutely. Yes, I think it's it's already slowly happening. Virgin Galactic and Blue Origin are the two companies which are sort of leading the way. Both of them in the United States right now. So, having the technology, as in with our company, to reduce the risk of spaceflight, because you reduce the complexity of the propulsion unit and also avoid the use of any explosive devices on board, is a fantastic first step towards provision of such a service with, regionally in here. So we are looking into that, but if I had $100 million sitting on my lap right now, I'll definitely want to work on that. But we have to take it one step at a time. We are still, what we refer to as seed stage.
And just going back to your slides, I think there was a slide where you mentioned 6 to 12% success rate, failure rate, right?
Yeah.
So what is your envision for ESS? What is the envision failure rate?
Envision zero.
Zero.
But realistically, we are talking about bringing this down to, for initial launches, probably to, hopefully to less than 2%. And as we iterate the technology later on, by the time anything that we build could be possibly human rated, we would have to be very, very, very close to 0% failure rate, which is what SpaceX achieved, but it took them quite a while. So hopefully we can do it faster.
Cool.
Yeah. All right. So I can see one question here. How are satellites brought back to Earth once they are decommissioned? Okay. So long story short, unless your satellite, let's say if it's a scientific mission that goes out to scoop up, some dust of a surface of a comet. If that is the case, then they are designed to actually conduct a re-entry. They have a heat shield and enough propulsive capability to get into the return trajectory. And then they are typically collected from either the surface or sometimes even captured in flight if the payload is particularly sensitive, to impacts. So very few satellites or spacecraft are actually brought back to Earth in a, from the reuse perspective, or to make sure that they are safe. Most satellites which are decommissioned are either left in space, they just shut down. They run out of propellant for their small maneuvers, and that's all you can really do with that. at that point. Or, well, some larger spacecraft like space stations are typically deorbited in a deliberate manner before they run out of propellant. And if they are already, they've outlived their utility already. Let's say they are getting old and not particularly practical anymore and outdated, and now you want to just deploy a new space station, for instance. They are deorbited in a way that basically they slow down on purpose. They fire their thrusters in their direction of travel to reduce their velocity and then re-enter the Earth's atmosphere. Typically, if it's done in a deliberate manner, they are basically they're allowed to just crash in a place that's called the oceanic pole of inaccessibility, or Point Nemo on the southern Pacific. That's the farthest point from any landmass, and that's where and basically there's no ship traffic going on in there at all. So if it's done in a deliberate manner, typically they are deorbited in such a way to crash exactly there. Yeah, so some spacecraft in geostationary orbit, they are too far up to use so much propellant to deorbit themselves because they are really high up. So typically they're actually sent into a higher orbit, so-called graveyard orbit, to free up an orbital slot for a fresh satellite. So yeah, it's a pretty controversial subject right now. There's a lot of talk about the space traffic management, so-called, who is going to be ultimately responsible for cleaning all of that stuff up. And well, from my perspective, that's actually good, because that only means that we have more stuff to launch. Because if you need to, if you want to remove a piece of space trash, you need to do it with another spacecraft. That's the only way. You have to send another spacecraft, and that means there's more demand for launch services. So that's actually, that doesn't scare me. I think eventually governments will form a fund to finance the debris removal, because ultimately we all rely on space infrastructure a lot. And it will become a public service, just like cleaning the streets eventually.
And there'll be another opportunity, space trash. Is there a danger of satellites crashing into one another when in orbit?
Yes, there is, and it's a danger that no one really wants. I mean, it's a pretty big danger. Yeah, because as you know, not all satellites travel in the same direction. Sometimes they travel, one goes this way, another one goes this way, and if they hit, the energy release. Well, yeah, basically do your math, how strong that impact is. And instead of having two pieces of space trash, which are just two satellites, you end up having a couple of thousands of smaller pieces. And that's pretty much impossible to remove unless it's low enough for orbital decay to take care of it. For all that residue of air resistance to take care of it. It's a massive problem. In fact, there is a theoretical concept that if this happens once, then all those smaller pieces traveling in slightly different trajectories can start a chain reaction, hitting more and more satellites and breaking them all up, and then leaving the entire environment unusable for a foreseeable future, which is a huge, it's a nightmare scenario, really. So space debris removal is pretty urgent. It is going to definitely happen. And for now, the best thing we can do is keep track of all the objects in the orbit and make sure that if we have a chance to prevent a collision, just do a collision avoidance maneuver, change the orbit slightly if there is a too high probability in the next, let's say several months, then that's what's typically being done right now.
Okay.
Okay. I love this question. Sorry, I really have to take this one. Is it possible to power a spaceship with nuclear power to reduce its costs? Okay, I'm a huge advocate of that. Yes, nuclear power can be used in two ways to propel a spacecraft. It can be done with nuclear thermal system, which means that instead of having a chemical combustion going on inside of a combustion chamber, you use that awesome heat from a reactor to heat up a gas like hydrogen and then eject it at a very, very high velocity. So that's one way to do it. And hydrogen is still, well, the thrust to weight ratio you could get from that is going to be probably close to 1. So it's a pretty quick maneuver. It's not going to be very useful for launch into orbit. Not vertical launch, maybe air launch. I've seen that show recently, and they did that, and that was pretty awesome. Yeah, but yeah, it will be a fantastic product for deep space transportation, actually. In fact, that's something I fantasize about building myself at some point. And the other kind of nuclear propulsion is to basically use a Hall effect thruster or an electric thruster. And instead of using electrical energy from solar cells, you just do it. You just use a small nuclear reactor to supply that electricity on board, and that means that even if you fly really, really far out from the sun, you still have a very good and stable supply of energy, because your solar cells become pretty useless once you cross the orbit of Jupiter. What's exciting about this is that you could gradually, slowly build up velocity to a visible fraction of the speed of light with this system and send a probe to another stellar system. How awesome would that be? So absolutely, yeah, I'm 100% on board with that. I would love to see that happen ASAP. And yeah, thank you for your question. That's a good one. Okay, what are the possibilities of low emission rocket launch? Okay, so this is where I will be very politically incorrect. Anything that burns stuff will produce exhaust gas. I mean, that's how rockets really work in the first place. They push themselves off their exhaust gases, and most of those exhaust gases are made of hydrocarbons, right? So you're talking carbon dioxide, a couple of other, effluents. There's really no way to prevent that. The best thing you can do is make sure that you're not combusting anything that actually produces toxic waste. Like some kinds of rocket propellant do produce highly toxic exhaust gases. Some very common solid propellants do produce hydrofluoric acid, which later deposits in the groundwater around the launch site. That is a problem. So the best thing you can do is just make sure it's as environmentally benign as possible. Doesn't produce anything that's actually toxic or super polluting, but yeah, there will be the exhaust products will definitely be considered greenhouse gases to some extent. But that said, I don't think the demand for launch will ever get to the point that this becomes a very visible part of our civilization's carbon dioxide emissions. It just doesn't have a scale compared to, let's say, electricity generation on Earth to become a visible problem. Okay, so next question: who bears the risk in case of a launch failure, the client or the company? You know who? The insurance company. Yeah, easy one to answer. There's always launch insurance, as long as you've done your job, a reasonable, due diligence to make sure your launch was conducted safely. The insurer will have to pay out. And launch insurance, believe me or not, space insurance is a thing. Okay. It's a huge thing. Alrighty, next one. Is there a possibility of space hotels that will be launched from Singapore? Why not? Why not? I don't see a problem with that. Space hotels, in the way that we like to envision them, like large, probably rotating space stations, like the concept from 2001, the Space Odyssey, for instance. It's those spacecraft will be really, really big, so you will want to launch them with a heavy lift rocket, not something that carries 150 or 200 kgs worth of satellites into orbit. But honestly, I don't see a reason why this shouldn't be done from vicinity of Singapore. As long as we have clearance to launch stuff in the area, like from the sea or from the Indian Ocean, then yeah, why not? Absolutely, why not?
So certainly a possibility. I think we have one last question. Would it be possible to colonize Mars as a second base in the current?
Okay. Wow, that's a big one. Look, getting to Mars is possible. Getting to Mars pretty quickly will be possible very soon. By pretty quickly, I'm talking about probably 3 to 4 months, because instead of going to the most energy efficient trajectory, you can just take a shortcut if you have extra propellant on board. So it's possible to shorten that travel time by just reducing the distance that's being traveled. Nowadays you have to go pretty much all the way around halfway around the sun before you actually catch up with Mars. In a so-called Hohmann transfer. I will leave that for another opportunity. But well, I think it was possible for a while now. With just the technology, it's really a matter of how do you of the capability that's required for it. We do have the means to generate electricity on the surface of Mars. We have solar cells which are good enough for that purpose. We have hydroponics technology to produce food in situ without bringing everything with you. Mars does have some ice, so you could actually refine liquid propellant out of it, liquid oxygen, liquid hydrogen. It can be done, but it's expensive. That's why no one really thought of it as a priority, because the space race basically ended in the 90s, and now we are in the middle of the second space race, and a lot of it is actually driven by private enterprise, which are more cost effective. So I'm I'm very optimistic about. I'm very optimistic that in the next 10 years we'll see technology that already exists, being fine-tuned for the purpose of colonizing Mars. And in fact, at this point in our lives, especially if you guys, the viewers here are, around the younger generation, maybe secondary school level, I think it's time to start looking beyond Mars already, because that's going to happen in our lifetime. And well, why not? Again, that boils to the simple question: why not?
Okay, so the answer is yes, but that's not a high priority right now.
Now it is. Now again, it is. For the first time since since the 80s, Mars is on everyone's. I mean, again, it's nice to have some competition going on between US and China, because now they are pumping a lot of money to their respective efforts to be the first ones.
Okay, so
everyone wants to be the first. So rivalry is actually healthy. Don't believe everything that people tell you that it's not good. It's actually very good.
Competition.
Yeah, it's the best for everyone in the long run.
Fantastic. Well, Simon, thank you very much for being here with us this afternoon and for sharing your information and insights. So thank
Pleasure.
you.
All right, thank you so much, Johnson. It was a great pleasure, and would love to be back sometime if possible. And thank you everyone for your questions. If you'd like to get in touch, you can contact me on my LinkedIn. My name and surname is the same as here, and you can also check out our website, www.equatorialspace.com, and stay in touch on our social media sites. So thank you so much. Have a great one.
The audience, if there are any more questions, please put them through to us on YouTube. The sessions are available. Look for Aspire Incubation Labs. Before we end, on the 1st of July, we have invited a very special guest on the show, NASA astronaut Jeff Williams. Let's watch this highlight.
Standing by. And liftoff. Jeff Williams, Alexei Yachtin, and Oleg Skropochka launching to the International Space Station.
This will be at 9 p.m. 1st July. If you have not already signed up, you'll be prompted to do so after the session. There is a link to do so as well in the chat. So I'll see you then. So with that, Aspire Week comes to an end. There are so many things going on in the aerospace industry: unmanned vehicles, reducing carbon emissions, battery efficiency, space tech. The possibilities are endless. I hope you have learned as much as I did in the past week, and I look forward to seeing you again next time. Take care. Bye-bye.